Contact resistivity is one of the most essential metrics to measure how easily that electrons and holes can pass through the interface of semiconductor materials. Traditionally, to get the resistivity, we need to measure the resistance across each two adjacent contact pads on the wafer, then apply line fitting to find the contact resistance. After that, we can derive the resistivity from it. So our target is to build a source measurement unit, aka SMU, to automate this process. So the goal is to make the SMU have a measurement deviation to be less than 10% comparing to the commercial digital multimeter. Our range of interest will be from 100 ohms to 10k ohms, and the project will scope from schematic design to the embedded development and PCB fabrication as well as the testing.
Welcome to Neuro's desk, and I'm going to give you some demonstration about what our SMU can do up to the recording date, which is the 6th of October 2020. Our SMU basically can measure 5 different resistors and calculate the contact resistivity from the measurement. As you can see here, we have 5 resistors set up on the breadboard to simulate the practical use case. And we are going to use a terminal command to communicate with the SMU, as it's the only way that we can talk to it bi-directionally. Let me open PuTTY for you. And pick our SMU. And power the SMU up. So, as you can see, we're greeted by the SMU, and we should be able to talk to it via text. Now, let's just tell it to do a measurement routine by typing TLM run. Enter. And you can see there are verbose output in the terminal from the SMU. They are mainly for debugging purposes, and also, as you can see on the SMU board, there are LEDs lighted up. They're indicating the relay, which is a white cube here, are active, and each active relays are selecting one resistor on this side. And by selecting one resistor each time, the SMU will measure the resistance value, and after the measurement routine, as you can see here, resistance values are displayed here in the terminal. And from those values, you can see the SMU calculated contact resistivity as this value, which should have a unit, and it will appear in the following days of work. Alongside the contact resistivity value, we have also calculated the R² value for the linear regression calculation used in contact resistivity.
When we use the SMU to characterize a solar wafer, we use a D-sub cable to connect the SMU and our newly designed Probe PCB. The Probe PCB has 12 TLM pattern probe to connect the TLM contacts on the wafer, 6 for measuring the current and 6 for measuring the voltage. Each contact has 1 current probe and 1 voltage probe to minimize lead resistance. To house the Probe PCB, we use 3D printing to fabricate a probe head. It can be installed on the arm of the probe station. The probe head has 3 different height settings for different length probes, and the probe PCB can be easily replaced in case the contact pattern gets changed. When doing the measurements, we operate the probe station to have the probes touch on the wafer contacts.
Our SMU can finish the measurement as fast as 7 seconds with a deviation of around 5%. This has met our objective already, so the next focus in our project will be the integration of the SMU and the touch panel display.